that you just took this past week, you were asked to find several things. You were asked to find the initial voltage here. You were asked to find what that voltage was as t goes to infinity, and you were asked to find the derivative of that voltage with respect to time at t equals 0 minus and t equals 0 plus. Likewise, you were asked to find the initial current flowing through this inductor here. You were asked to find the final current as t goes to infinity, and you were also asked to find the derivative of that current at t equals 0 minus and t equals 0 plus. So just like we have done on all sorts of problems similar to this, we want to go ahead and draw what that schematic will look like at t equals 0 minus. So here's what we have. We have our 6-volt source, that stays on the whole time. We have our 1 kilo ohm resistor, that stays. Our 2 kilo ohm resistor, that stays. And we know at DC steady state, which is where we will be at t equals 0 minus, this capacitor behaves like an open circuit, the inductor behaves like a short. So that's what we have right here. We also know that this voltage source is given by the formula 3u of t. So at t equals 0 minus, that is right before that turns on. So since it's technically off right there at t equals 0 minus, we draw that as a short circuit. So this is effectively what we have. And so we have 6 volts here, we have 1 kilo ohm down here, we have 2 kilo ohms down there. You'll notice that since the inductor is behaving like a short, effectively the voltage across the capacitor is in parallel with the voltage that we're going to see across this 2 kilo ohm resistor. So we can basically consider this to be a voltage divider with a 6-volt source and dividing the voltage amongst a 1 kilo ohm and a 2 kilo ohm resistor. So that means we get 2/3 of the 6 volts across the capacitor initially. We also know that capacitor voltage does not instantaneously change. So if that's what we have at t equals 0 minus, that's got to be what we have at t equals 0 plus. So the first answer here is 4 volts. We can also look at this initial current right here and realize, well, this just now looks like one big loop. And so that one big loop has a 6-volt source and a combined 3 kilo ohms of resistance. So if we just take 6 volts divided by the combined 3 kilo ohms, that means we've got 2 milliamps running through this loop. That is the current through the inductor at t equals 0 minus, and we know, based on the properties of inductors, that inductors do not instantaneously change current as t would go from 0 minus to 0 plus, so our initial condition for our current also must be 2 milliamps. So those are our initial conditions that we have for the voltage. Now, we can get some of our initial conditions for the derivatives here based upon thinking about what is actually happening at steady state and what's actually happening as soon as we transition into turning on the other voltage source and currents starting to flow in different directions than maybe they were before. So if we think about this dV dt at 0 minus, what do we mean by things being at DC steady state? That means that that capacitor has already reached full charge. There's no current flowing through it, and we know that IC equals C dV dt. Well, if there's no current flowing through it because it behaves like an open circuit, then you have 0 amps equals C dV dt at 0 minus. So therefore, the change in voltage with respect to time at 0 minus is simply 0 volts per second. Likewise, over here for the inductor has 0 volts across it at t equals 0 minus, and we know that VL is equal to L times di dt. And so at 0 minus, there's no voltage across it. It is not a 0 Henry inductor. In fact, it's a 1 millihenry inductor. And so we know if 0 is equal to L di dt at 0 minus, then that means that di dt at 0 minus is 0 amps per second. So that's what we have here for our initial condition for the derivative. Now, we need to go into the t equals 0 plus circuit and start looking at what's actually happening to figure out where the currents are going and where some voltage changes might be in order to understand what our derivative is going to be at t equals 0 plus. So this is what our schematic will look like once we get into t equals 0 plus. We've still got this 6 volt supply. We still have the 1 kilo ohm and the 2 kilo ohm resistor. And now the inductor can have a change in voltage. It cannot have a change in current. So we know there's still 2 milliamps flowing through there. We have this capacitor which can have a change in current, but it cannot have a change in voltage. So we have this capacitor that could have some current going through it, but we know that it is maintaining the same 4 volts across it that it already had. And so we know there's 4 volts across there. So if we label this node relative to a reference node down here at the bottom, we can say, well, this node has 4 volts. That allows us to figure out how much current is flowing through this 1 kilo ohm resistor. The 1 kilo ohm resistor goes from 6 volts of potential over here to 4 volts of potential over there, meaning it's dropping 2 volts of potential across a 1 kilo ohm resistor. So 2 volts divided by 1 kilo ohm means that there's 2 milliamps of current flowing through there. We already determined that there's 2 milliamps of current flowing through this branch over here, and that, because everything is in series, even though this voltage source is turning on, this inductor has to maintain 2 milliamps of current going there. Now if we do Kirchhoff's current law right here at this node, we've got 2 milliamps coming in here, we've got 2 milliamps of current going out there, and that lets us ask the question, well, how much current is now flowing through the capacitor? Well, we've got 2 milliamps coming in, 2 milliamps going out. The only amount of current that we could have flowing through that capacitor is still 0. And so we have 0 amps of current through the capacitor, and IC is equal to C dV dt at 0 plus in this case, and IC is 0 for a non-zero capacitance, so therefore dV dt at 0 plus is also 0 volts per second. Now, that is not the case in terms of the di dt. Let's look at what's happening over here. And so now in this case we know we still have 2 milliamps flowing through this whole branch. And we can actually do Kirchhoff's voltage law around this right mesh. And so we recognize the mesh current is 2 milliamps. And so we have right here minus 4 volts. We know we have 4 volts across the capacitor, plus whatever the voltage is across the inductor. That's what we're going to solve for here. Plus 3 volts, plus, now we know this has to be 4 volts because we have 2 milliamps of current going through a 2 kilo ohm resistance. So 2 milliamps times 2 kilo ohms gives us a 4 volt drop across this 2 kilo ohm resistor here. So if we have minus 4 volts plus VL plus 3 volts plus 4 volts equals 0, then that means that VL at 0 plus has to be minus 3 volts. That's how we balance out that equation. So VL is minus 3 volts. That has to equal L di dt at 0 plus. And so therefore, to figure out di dt at 0 plus, we simply take negative 3 volts, divide it by 1 millihenry, and that gives us negative 3,000 amps per second. So our initial condition at 0 plus for di dt is negative 3,000 amps per second. So now we have figured out the V at 0 plus as 4 volts. We've figured out the derivatives of the voltage with respect to time at 0 minus, 0 plus. We've figured out the derivatives of current with respect to time at t equals 0 minus and 0 plus. And we figured out our I at 0 plus. The only thing left to figure out on this first problem is what is our steady state condition. What is the voltage as t goes to infinity? What is the current as t goes to infinity? So we go down here to this schematic representing what happens as t goes to infinity. It's very similar to what we had at t equals 0 minus, with the one major change being that now this 3 volt source is turned on. So now we once again have the capacitor in DC steady state, so it's behaving like an open circuit. We have the inductor over here in DC steady state, so it's behaving like a short, and we have a single mesh effectively that we can analyze. Okay, so in this case we want to figure out, well, what is the current that we have there? Well, if we combine these resistors in series, we combine the voltages in series, we know that we have a net of 3 volts of potential, because we have 6 volts here, it's opposed by 3 volts there. We have a total of 3 kiloohms of resistance, and so our current is going to simply be 3 volts divided by 3 kiloohms, which gives us 1 milliamp. And that amount of current is what is flowing in this whole loop. That amount of current is what's flowing through the inductor. So our I of infinity is 1 milliamp. Now, we also want to know what is our voltage here. Well, in this case, if we have a reference down here, which is what the reference is for this, we are gaining 6 volts of potential here, so this would be a 6 volt node. Then we have 1 milliamp of current, and we happen to have a 1 kilo ohm resistor, so we know we are dropping 1 volt across this. So we are 1 volt less than the 6 volt we have here, so V at infinity must be 6 minus 1, or 5 volts. So the right answer here for V going to infinity is 5 volts. So that is our solution to problem number 1.